Hi everyone, Greg here. Today I'm going to talk about recursion, mastering recursion. Now, what recursion is fundamentally about is a function which does call itself. Now, I don't think I'm being controversial here by saying that there are many different levels of proficiency when it comes to programmers. To my mind, they fundamentally fall into three types. So firstly, you have the novice. The novice doesn't really know anything. And I don't say that to throw shade at them. I know we all start there. But they really have the wrong idea as to what programming really is. They believe programming is about writing code. They think they will become a good programmer simply by getting to know the programming language very well. And their idea of being a great programmer is to know a lot of different programming languages. Above that, you have the competent programmer. The competent programmer understands that coding, that programming, fundamentally is about problem solving. It's not so much about writing code. Writing the code is a means to an end. The competent programmer will know all of the fundamentals to his trade. He will know about data types. He will know integers and floating point. He'll know the basics of how they work, the strengths and weaknesses of each one of them. He'll know the data structures like the array, the linked list, the binary tree. He will know their strengths and weaknesses and when to use one and when to use the other. So in engineering, be it software engineering or really any other type of engineering, a big part of designing is managing trade-offs. And the time-space trade-off is a well-known and a very common one in software engineering. And to make decisions when you design software is basically oftentimes about balancing those trade-offs. A competent programmer will know the most common, the most important algorithms like the binary search and the quicksort. I will show you a binary search in a minute. The competent programmer knows the basic concept behind everything that's involved in computing, like databases, networking, etc. Now, the field of computing is too large to know everything about all of those topics, but it's important to have at least the basic notions down. Now, the programming language really should be trivial, especially if you have a good language. Imagine writing with a pencil. When you write with a pencil on paper, you're thinking about the content. You're thinking about what it is that you're writing. You're not consciously thinking about how you move your muscles, how you need to trace that line, etc. That is done by the subconscious part of your brain. If you have a good programming language and if you know how to code, you're focused on the problem, and the programming language will melt into the background and you're not even going to think about it. If you have to spend too much time learning the programming language, you basically have a bad programming language. Knowing how to code is about the things I've mentioned above, like the data types, the data structures, etc. And therefore, from one programming language to the next, those things are more or less the same, right? You have in a new programming language, you have different keywords, different syntax, and this is something that you should be able to learn in an afternoon with a good book and a cup of tea. Maybe some of the old programming languages like COBOL, they have like a lot of syntax. You might need 2 cups of tea to learn that one. But by and large, you should be able to learn the language itself very quickly. And if you can't, it's either because you don't really know how to code or because the programming language is bad. So then, above that, you have the grandmasters of code, and those obviously know everything that a competent programmer does, but on top of that, they can do difficult jobs. They can write their own PNG loader, they can write their own font renderer, a game engine, or stuff like that. And maybe they cannot do all of those things, but they can do at least one of those kind of things. And of course, they can handle recursion without problems. Okay, so the main thing to understand about recursion is that you never technically need it. And most of the time, it's a bad idea to use it. I will give you a couple of examples later where I think it is a good idea. most of the time it is not. There is something known as the Bohm-Jacopini proof, which basically demonstrates that every single algorithm can be written using only the sequence, the selection, and the iteration. So the sequence is basically writing one statement after the other. The selection is basically the if and else statement, and then the iteration is simply a while loop. So with just those three, you can, in theory at least, write every single algorithm you may ever want to write. So recursion is never strictly necessary. So when it is a good idea, the function is called relatively few times. I don't want to put a number on that because it depends on the specific situation you're dealing with. Just a few times. You have inside the memory, you have something called the stack, and the stack is that which keeps track of the functions as they're being called. It stores the local variables and things like that. The stack grows towards lower addresses. So basically what that means is that the stack can only get so big before you no longer have valid addresses, and the stack is no longer able to grow. So you can do you can blow through your stack when you call a function too many times. So you just need to be aware of that. Where I think most people struggle is because they're trying to follow the code line by line. When you do that with recursion, things get confusing very fast, and basically you're not going to be able to do that. So what you need to do when you design a recursive function is you just need to focus on those two questions. And I am going to write recursive functions, so with examples this might make more sense, but you ask yourself exactly what should the function do and what is the break. The break is that which prevents the function to be called over and over and over again. So there will be an if statement, there will be some condition. Once that condition is met, you don't call the function anymore. So what I am going to write is a factorial. The factorial is one of those examples where it's not a good idea to write it recursively. I'm going to do it in this case because I think it's a good demonstration. So what is the factorial? It is written with that exclamation mark. This is 4 factorial. That's how it's read. It's very easy to understand what it means. 5 factorial is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So the idea is very simple here. 1 factorial is 1. That's also not hard to grasp. 0 factorial is 1. And this is true by definition. That is tripping a lot of people up because it seems to break the pattern. And well, technically it does. But this is true by definition. So that's the iterative definition. Now the recursive definition. What is n factorial? It is n, that number n, multiplied with the factorial of n minus 1. So this is recursive because in order to explain what a factorial is, I again use the factorial. It is a self-repeating pattern. It's referring back to itself. And here we have the break. So the factorial of n minus 1, once that n is as low as 1, then we'll just return 1 and we will no longer call a factorial. There's no factorial here in that definition here. So let me write this factorial function, the 2 factorial functions. So I'm going to start with the iterative one. I'm just going to abbreviate that like this. It's going to take one variable n. So how do I start? I'm going to have a variable to store the result. So there we are. You notice that the recursive function is a lot shorter than the iterative one. This one is less efficient, however, because there's this hidden cost of putting those functions on the stack that C gives you for free. So it doesn't mean it's more efficient. So now what if I actually test this? So I will do. So I think that should do. So let's try and compile this now. Okay, that seems to have worked. So now, okay, and then it does run both those functions, and obviously the answer is the same. Okay, so just one thing I've added here is this n bigger than 12. If n is bigger than 12, then we have overflow, and then you return -2, and here too as some error code to indicate that basically we had overflow and it's a number too big than we can calculate. Now obviously this is not the right way to do the factorial. This is not good code and I don't recommend you use it, but I've done this just to demonstrate how recursion works. And this function, it may well be simplistic, but it does have the advantage that it's always going to work, or always going to behave in a way that is appropriate. It will always either return the correct answer, or it is going to give us an error to let us know something went wrong. So this function, as primitive as it might be, it does work. Okay, so now I'm going to do the Sierpinski triangle. I always like to start from a Hello World program, so I got this program over here. I am going to compile it just to see that everything is working properly. I am using the Cairo library. So like this. And now I am seeing that this hello.png was created. I can have a look at that, and there you go. And what I'm also going to do is I want a square canvas, and I'm going to make this a macro. That way I can easily change the size of the canvas. So let's just say 500 for now. Okay, so that should give me a plain white canvas, and then here I'm gonna do draw triangle. Okay, so I've written this function draw triangle. There is nothing fancy going on here yet. I just want to draw that first big red triangle that will later then be subdivided into the smaller pieces. So basically I take 5% of the side of the square and I put my x1 point there. So I do that so that when I later change the size of the canvas, I always get my triangle in a nice location. This is just setting the color of the triangle. This will be the second point that will also be part of the base. It'll be on the other side of the canvas. And then here I'm simply using Pythagoras to figure out what the y coordinate is of that point in the middle on top. So that should draw us our triangle. So let's try this. I'm going to compile this. What I've added here, -lm, this is the math library because I'm using a square root, so I have to add this in here now. So this has compiled, and now if I look at the actual image, I should see a red triangle, and there we are. So what is the next step? It is to draw the smaller triangle, the white triangle in the center. How will I do that? I need to take the midpoints of the three sides of the triangle and use those three midpoints to be the vertices of the new triangle. So I'm just gonna from here draw smaller triangle. This will be the recursive function, and I'm just gonna pass on the coordinates so I can compute the midpoints of those. And now I simply need to, well, I need to set the color as well. Okay, otherwise I just draw a red triangle over a red one. There. And that should be my first white triangle. What I have here is not yet recursive. I'm just doing this one step at a time. Just want to make sure that at each step it is doing what I expect it to do. So I'm just going to put the prototype up here. Yeah, and I'm going to recompile this. I'm going to look at my image again. Oops. Okay, that's not what I expected. Oh yeah, I know what I did. Hold on. Obviously, I had to use the mid. Okay, so you see, it's good to check at every step that you're indeed doing what you think you're doing. So now we have a much better result. So in order to draw a complete Sierpinski triangle, I just need to do the same step and repeat. By having drawn this white one here, I've subdivided the big triangle into 3 smaller ones, right? And so now I just need to repeat that procedure on the 3 smaller ones. Now, what is going to be my break here? If I want to draw a mathematically perfect Sierpinski triangle, I need to do that process infinitely many times. At some point, the triangles get so small that they're smaller than a pixel, and there's no point in drawing it any further. So looking back at my code here, one possible break I could include is I could just say if x2 minus x1 is smaller than 1 pixel, then I quit doing it. That is a break that I could include there. Or I could do something much simpler, which I'm going to do this time. I'm just going to decide to go a certain number of levels deep. Actually, yeah, I'm going to do it. Certain number of levels deep. Two. So I'm just going to remove one, decrease level by 1, and then if level is smaller or equal than 0, then I turn. Okay, so that's my break. It's not yet recursive. This function is not calling itself. So I'm doing this. Draw a smaller triangle. What am I performing this function on? I need to do it on that smaller triangle. So this is x1, y1. This is x3, y3. So I need to, the first triangle, use this, and those are 2 midpoints. Okay, there we are. That's our nice triangle. So now that we have the basics, we can go crazy if we want. The rest is very, very simple. All I have to do now is increase the level. So let's go 10, level 10. And now I should have a really nice triangle. And if I want to make it bigger, $15. And so now I have it on a bigger canvas. So there you are. That's your Sierpinski triangle. All right. So the last thing I want to show you is the binary search. So what is the binary search? The binary search assumes that you start with an array, a sorted array. So if you look, all the numbers here are in the right order. Let's say that I wanted to find number 7 in that array. What would I do? I would jump to the middle element here and I would check, is this 7? It's not, it's 32. Okay, the next step then would be, given that it is a sorted array, where would 7 be if it is in the array? Would it be after this point or before this point? So clearly it would be before this point. So then I take the middle of that, which is 7, and that is actually the number I was looking for. So at that point it would just return 2, right? Imagine that if this were 9, for example, well, no, actually let's say 6. If this was 6, for example, then I would judge that the 7, if it is in the array, would come after. So but I've already checked this. I would take those 2 here and I would take the middle. Now there's no real middle here, but I would just take either one of them. Check that one, and then if that's not in, I just return -1. Say, hey, 7 is not actually in this array. So when we look at that, what are our 2 questions? What do I use as break? The break is either found the number, or the break is can no longer subdivide the array. And what exactly does the function do? Takes middle element of the array, then checks if this is the number, if so, then you just return. If not, apply same function to, how would I phrase it, to first or second time, to previous or next section. That might be okay. So this is what we need to do in code. Okay, so now how am I going to design this binary search? I'm gonna have a function binary search. It's going to take as argument the array. It's going to take the size of the array, and then the number I actually want to find. So let's say 7, and it will return the index, and the index is where 7 is. So and then it will return -1. So if right? So this, if there's any kind of error or if the number is not found, it will return minus some other number, but it's going to be smaller than 1. So it will, the number not found, it will return the index where the number. Okay, so we can write our prototype here. Okay, and here now I can do a couple of sanity checks. So if the array is null, then I have error. If size is smaller than 1, error as well. I think I also want to allow for the size just being 1, because in that case there's no point going through that entire recursive procedure. Okay, and now I'm actually going to call this the recursive function. I apply it to the array. Tell it what to look for, and then I have to apply it on the remaining section, which for now is the entire array. So what I have here now is this recursive function, and I have the start index and the end index. This is the section that I'm gonna have to be working on. So what is the first thing I'm gonna do is I'm gonna compute the middle of that array. So if that element that I'm looking for is indeed in the middle, then I need to return that index, and then I'm done. Now, if that is not it, then I have to ask myself, okay, this element in the middle, is it bigger than what I'm looking for? If it's bigger than what I'm looking for, then I have to do that same procedure on the first section, the section that comes before it. So that would be array, find, it would be start and middle. Else, and if I'm in the else, then this thing is smaller. Okay, we've ruled out being equal already. If it is smaller, then that means that what I'm looking for, if it is in the array, will appear in the section that follows. So that's middle and end. Okay, so that should be roughly it. Okay, I don't need to check. Now that middle element itself, I don't need to check anymore, so I can actually go one past that. Here, -1. Okay, so now there's just one case I need to deal with, and that is this won't work very well once I've narrowed it down to just two elements within the array. So what I'm gonna do is if int minus start is smaller than 2, neither of those are true, and okay, so let's test this now. Okay, the number found at 2, 0, 1, 2, so where it's supposed to be found. Let me just put a mark. What if instead of 7 I want to find 42? It's finding it. 6. What if I put something in that cannot be found? Number 9. Okay. So that should give you a couple of examples of how you do a recursive function. We have seen the factorial. It was not a good example, but a simple demonstration. We've seen how to draw a Sierpinski triangle, how to do a binary search. I will have the code for all of this available on the GitLab. Hope you enjoyed this. I hope you learned something, and thanks for watching.